I see your lovely faces, so I will start off from there. Hi guys, so my name is Emmanuel Bakare. Folks call me Backman, and my experiences are so. I will be taking you on networking stalemates. This is not a friendly networking engagement where you meet a guy and you don't like him. No, this is actually more on computer networking. The kind that you barely see every day but powers most of your lives, from TikTok to Google to YouTube. This talk is going to be focused on closed-weight sockets. Now, this makes no sense to probably most of you, and you probably have no idea what it is. But after this talk, you probably will. The idea behind this is that every single request you make, from your laptop to a server and back, for those of us who are engineering focused, we already know that. For those of us who are probably not, every time you make a request, there's something called a socket. Think of it like a door. From it leaving your laptop to going to google.com, Google has to know that it's your laptop that sends the request, and that is their server that was meant to get the request. So that's the socket, right? Think it's exactly a door. You walk through the door, you get to google.com. You walk back the door, you get your laptop. Now, closed weight, what does that mean? In simple terms, it's basically the door is half open, half closed. Normally, the door should be closed once you're done getting to google.com and it's coming back. But for some reason, it's closed waiting. Like, what's going on? The door is meant to be closed because google.com is no longer talking to you, but it's not. Now, that's a problem. And why is it a problem? Because it means that if someone else came to the door and tried to use that same door to access google.com, it won't work. Meaning that what? We've broken the server. There's no way to talk to each other anymore. So that's the idea of closed-weight sockets today. I'm a senior DevOps engineer. I like to say I'm a salesman first, engineer second. But my background is actually in electrical engineering. I studied at Unilag. No offense to other universities. All of that is not on the slides, but let me push that back up. So yeah, I'm a senior DevOps engineer at Twilio. I used to do networking at AWS. I did networking there for 2.5 years, basically powering terabits of traffic. If you've ever heard of terabits, you probably don't even have, well, sorry to Lagos, you don't even have megabits of throughput, like it's bad. So that's like orders of 6 magnitudes more, right? We've seen things break, and this was an issue I had there. Once you begin to do things at scale, that closed-weight socket thing, because it's so quick, imagine thousands of you trying to go through that door and the door closes suddenly. What happens? Everything breaks. It's chaos, right? Because it's what? It's trillions of people trying to access one single thing at a time, and that thing cannot respond. It's obviously going to go somewhere. So that's what closed-weight sockets are. Follow me on Twitter. I'm at Bakare. I post a lot of stuff. I should post sometimes. You might like it, you might not. At least you find out then. So let's get into it. IP transport protocols. Now, all of this is very big words, but the idea is networking is in 2 layers. TCP and UDP. TCP is the guy that we all use today. UDP, not so important. I'll leave that out of that. But the idea is that there's a bunch of things that are in that same light. I'll mostly be focusing on TCP today. Now, when we think of TCP, TCP is basically the handshake protocol. What that means is that whenever you send a request to google.com, google.com is going to respond back. Google.com will always respond back. TCP has strong transactions, meaning that as far as that request was sent out, it's always going to come back. That's why the closed-weight thing happens, because google.com is like, where is the guy that sent me a request, right? Why is the door closed? So it waits, because it has to deliver that no matter what. And that obviously brings its own problems. Now, thinking about it, there's a bunch of TCP states. Closed is the pretty simple one. Closed is that we were done and we closed the door. Closed-weight happens because the door got closed before it was done. Now, someone is trapped on the other side, either the client or the server. That's you walking in or the guy delivering the request to you. Listen is basically simple. It basically happens whenever you start a server. For those of us who have ever run Python, Golang, anything that started a port that you accessed, it did that and established this from the client side. So listen is, I open up the door. I'm the waiter by the door. I'm the security guy. I'm listening for what? Somebody to come in and establish a request to me so that they can walk in. You are the client. The gate man is the server. And the door is TCP. It's all beginning to make sense, right? What happens when the door doesn't open? The gate man says go through, but you can't. That's the entire basis of this session. So let me dive straight into it. There's a bunch of fancy diagrams here that is drawn together. I got this from Wikipedia. But it kind of gives you an overview of like how the entire thing works. You see listen up there. Whenever you see the blue lines, that's the server. So you can see the server listens. The client sends a request. Most of you know SYN, ACK, all those parts, but it's not important. What happens when the connection then tries to close? Right? When we've done our transactions, like a waiter at a restaurant, you've made your request, they've delivered your food, they're trying to close out the tab, but you're nowhere to be found. Or the server is nowhere to be found. You're stuck waiting at the table. That's another example of close wait. And this is where we'll be focusing today. What happens when the server is trying to close the connection, but the client isn't responding? I have a very fancy diagram here of what close wait would be. But first, a description in a more technical term, if you've understood it. So close wait basically means that the server has received the first FIN, meaning that the server is trying to close the connection, and the client is in the connection of being closed. So you are basically telling the waiter, I want to close this request at the restaurant. The waiter is like, I will close your request, but then the waiter never comes back. Right, that's a very good example of this. So that FIN is you telling the waiter, I want to close this. And if you look back up here, you see that nice FINAC right there from the server side. That's that blue line from established. Now, it's a passive close. And the reason is because if you go to a restaurant and you sit down, you end the tab. You basically go and say, I want to end the connection. Usually, that's what happens, right? Close wait happens when the waiter at the restaurant is like, that's the server is like, I want to end you being at the restaurant. Now, that is very awkward. That never really happens. And that's the basis of the transaction model in networking. In networking, the expectation is that the person who made the request should be the one closing the request, right? Because it's transactional. If two people can close the request at the same time, you end up with a edgy bit of consensus distributed systems problems, because did the server ask for it to close first? Did the client tell it first? We don't know, right? They're far apart, worlds apart, in fact. Sometimes even all the way in space and back. That's the examples that close wait kind of causes. So let's push it down. So it can be in close wait indefinitely, because remember, the door is closed. The waiter and the client can't talk to each other anymore. So let's keep it going. Let me show you a diagram, which is nicer. So client and server are trying to talk to each other. They do something called a three-way handshake. I shake you, you shake me, we smile at each other. That's a three-way handshake. They call it the SYN, ACK, SYN, ACK. Synchronize, acknowledge, synchronize, acknowledge. Then both of them are established. You see the client and server on both sides, and that basically tracks what we call the TCP state, what session they are in. We continue down the line, connection is established. Now the client is like, okay, I'm done. I'm done eating. Let's make this a restaurant example. Now the FIN goes, and the client goes into FIN wait 1. That's the first state. You told the waiter, I want to end this meal. Please bring me the bill. The waiter is like, okay, I'm going to do that, but before I close your tab, I have to wait, right? I have to run over to the tab, I have to get your bill, then I'll come back and tell you, this is done, you can head off. Obviously, there's a problem here. What happens if the waiter goes home? No one ever thought about that. Or what happens if you run away? You leave the restaurant. I'm sorry, no offense to anybody here. So what happens now is that the client goes into FIN wait 2. In TCP, there's a very weird problem that they did. It was a very smart time. It was a smart thing at the time they did it. They were like, the client is always going to start the request. Because back in the days of RPAR, I mean, they had one megabit per second was very fast. So requests didn't happen that quickly, right? People didn't have issues. Connections were like you to you, him to him. They were very small. So they never thought about the fact that could the server and the client disconnect? If you've ever had to use your network on your mobile, you discover that a lot of times the network can just end. MTN can decide to be funny. Tinubu can decide to turn off Twitter, right? Things just happen. It's just all over the place. So the FIN wait 2 happens because the client is like, I can't connect anymore. But the TCP guys were like, the client can terminate the connection if it wants to. So the client has an active close. If I am at a restaurant and the waiter doesn't come back and I wait long enough, I'm just gonna leave. They can't hold me. But the server has to pay for that bill. You see where I'm coming? There's that transaction model. The client isn't held if the connection terminates, but the server is. And that's where we then get to this problem. So you send a request from the client to the server saying, I want to end it. The server sends back an ACK. That's FINAC. It's saying, okay, fine, it's done. The app is ready to close, but you notice that from that close wait, it's waiting for the app. You don't see anything on the other side saying wait for the server. And that's the problem with TCP today. So this problem actually happens a lot, but it doesn't happen frequently. It doesn't happen with your phones or laptops or anything. It happens on really big servers, like AWS's scale, where you have like thousands, if not millions of machines transacting every day. And sometimes your phone can trip off, right? But because you are all so many, it means that a door that was meant to work for one person, and then obviously there's like thousands of doors. Imagine if hundreds of them begin to close at once, right? What happens is that those transactions, those requests fall over to the other guys, and then everything then backs up. And then obviously that's how things fail. So that's the problem with closed-weight sockets. They take up resources without providing any value. Why? Because the server is waiting for an application that does not exist anymore. So new guys can't use those doors anymore because why? Only one person can fit through the door at a given time. And that's where we're going to go straight into it. So that's the problem about them. Closed-weight sockets cause issues. They take up resources, they cause memory leaks, they cause resource leaks. Things you don't really need are being allocated to resources that aren't really being used. You have doors that are closed for people that are trying to pass through. It's all backlogged in there. So I'm going to skip all the slides because not really a lot of it is really important, and I'll dive you straight into a demo. Now the demo is going to be quite simple with some comedic factors to it. So let's dive into it. So what I have here is a server that I built. Now, the problem with closed weights, if you probably not noticed, is that the client is always fine. TCP, when they built the protocol, they were like, the client is always going to be correct. The server is always going to be wrong. So this is my server. Now, what have I done? I've set the max connections to be 10. Now, why is that? Every server has a max amount of things it can handle. If you have one door and one person can go through, your throughput is 1. You're never going to beat 1, right? It can't handle more than 1 connection. In my case, I have a server that can handle 10 connections. So I've got 10 doors. Now, the idea is that on a normal day, if I'm making multiple requests, it should go through those 10 doors just fine, right? If you walk through the door and it's not closed waiting, you walk out, it gets closed, and someone opens it again, right? That should be the flow of it, right? You go from listen on the server to established, and from established, you begin to then transact as usual. Now, the problem here is that, in my case, I've already built this server, so you can see I have some low level, but it's not really low level, just some networking stuff. I have some socket, we use the address, blah, 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 all the fancy stuff. But you notice here, I have my stuff, I'm accepting connections, and then I'm, counting a bunch of things, right? So this is going to be interesting. This is the guy that is causing my closed weights. So in some cases, closed weights can be due to a server bug. So you might think this is actually very fancy, but when you think of things like PostgreSQL, Redis, this is actually the behind the scenes framework of how they work. Like, it's not magic, it's all still code. The port is 5555, I could have made that 6379. And you send a request in Redis, they have their protocols, it's just text. If you've ever looked at any HTML request, it's really all just text. And this is all they do. You send the request to the server, they get it, they push it back. So I'm going to show you this. I'm creating multiple processes per each request. And then here I'm checking, if it's too much, then we cancel the request. Now, what I have here is that I have this guy that's handling every connection up here. It gets the page, it logs it, and then it kills it. So why does it kill it? Remember what we said about closed weights is that either the client or the server goes away abruptly. Now, I can't affect the client because it's not easy, but I can affect the server. The server can go home, or in this case, he died and went to heaven. So we can take it from there, right? So let me jump into the demo for you guys. So here I have this bunch of servers, right, that are running. So this is actually the server. You can see my cow here, cow say. I could also change this to cow think. For those who don't know, this is on my Ubuntu. So I can just say this is the server. And now my cow is thinking this is the server. Now, what I have here is a very simple setup. I'm watching connections. You see that I have 4 connections in established, meaning that I have some things that are working. If I come here and I start my server, which is this guy, this closed weight server here, is the exact same code. This is running on a Docker container. So I'm using this to, illustrate the server. And I'm going to basically do some Python 3 closed weight server. You'll notice that there should be a listen up on there very soon. Up on here very soon. Where is it? That should be there. So yeah, it's actually here. So you can see the listen, right? That is open. So that's my port. That's my 5555. Now, what I have here is the server. This is my client. Now, on my client, you can see I have a bunch of things working, right? I'm also watching connections here. I'm going to start this again. If it picks up. Yeah, that does take a while. But here you can see that I have a bunch more connections on my laptop, because I'm doing a bunch of things. but I don't have a server running, so there's no
so
difference.
many times as well.
Now, what I'm going to do here is that this server is running, right? I can actually ping it with like nc localhost 5555. I can do all of this, and here you can see that the request would come in. You can see the logs here, right? Connection from this guy with this port, everything else, child process will be stopped. Processes with close wait is 2 out of 10, right? Now, what this means is that I have 2 processes that are in close wait, right? Because this is the buggy server. This client is waiting, right? So now it's waiting for the app to what? End the connection. So this is my client. This is the guy making the request. This is you on google.com making a request to google.com. Now, this client needs to send something, but it's not going to send anything, right? So if I come back and I close this, you will notice that we have some states here, listen, we have some established. If I cancel this, you will notice that we have a close wait opening. We have a fin wait 1 and fin wait 2. Remember that thing I was telling you about fin wait 1 and fin wait 2? The client was like, I'm done. So he created a fin wait 1. Then he waited a bit and it was like fin wait 2 because he couldn't find the server anymore. And why couldn't he find the server? The server died, remember? I killed it. And now we push into this side, and then what happens? There's a closed wait socket open here. Now, what happens if I send thousands of requests? Can anyone guess? Your server will hang. Exactly. So let me do like no block, right? This is thousands of requests. It could only handle 10. Because remember, I can only handle 10 connections at a time. Only 10 of you can walk through that door. So what now happens? I have thousands of requests here that are waiting for forever to load. And there's also another interesting thing that is going on. So whenever closed waits happen, you get a bunch of requests here that are just pending. So now you can see how many instances of my closed wait server is running. 12, 13 of them. Now what happens if I create thousands of them? The instance is just going to die because there will be so much resources being used for requests that are not really being used. So this is the problem with closed wait, right? It's very bad. Now, how do we fix it? Obviously, when I was writing this server, I obviously made a bug, right? I came here and then I was killing the process indirectly. Now, this could also be something down the line. It could be NAT rules. It could be like you send the request out, there's firewalls blocking the request from coming back in. Right? As far as there's anything that makes the client and the server unable to talk to each other, you will get a closed wait socket. And as you can imagine, that's bad, right? So now I'm going to comment out this guy, right? And then I'm going to copy it back into my guy. So I'm going to do a docker cp. Where is it? So in this guy, I already have everything set up here for anyone that wants to test it. I am going to copy this new server onto this guy with the fix. And what is the fix? I'm like, okay, fine. I'm not going to kill these connections anymore. In some cases, it could be you updating networking rules. It could be really a lot of things. So I'm going to run this guy again. You notice that when I close the server, those closed wait guys disappeared. Like if you notice. Because why? It is bounded to that server instance. So you can restart the server, but again, it doesn't fix the problem because once thousands of you send requests again, it stops. So you can see how malicious it can be. And remember, every time a new server gets that closed wait, the door closes, the next one gets the traffic. And what happens when you're in AWS? Oh, sorry. So let's actually take this off. So now I've fixed my bug and I'm going to run this again. And what happens? 1 out of 10, 1 out of 10, 1 out of 10, 1 out of 10. Looks like the server is fine now. We have some closed waits, but you notice that they're closing properly now. Because the server can respond back. The client can respond back. So that's the general idea of like closed wait sockets and how they happen, how they can be malicious, how they can cause problems, how they can basically force your entire server to go down without you even having an idea. Now, you will notice that this was only possible because I knew the fix. Most of you would have gone, it's not responding. Restart it. Restart it. It's not responding again. Restart it. It's not responding. And that's how malicious this is, because it's very silent. There's no error about any failures. It's just what? You've used up all the connections. Now, what would you do if you're in my case? You would say double down. Double it and give it to the next person. But that doesn't work here. So I already explained fin wait 1, fin wait 2, and closed wait, right? So now you understand what closed wait does. You understand how bad it is. You understand how impactful it can be. You understand the issues that can come about when you're working at large-scale systems. And for that, we're kind of getting to the end. With closed wait sockets, a new process is spun up for every request. It doesn't clean itself up. Memory leaks, resource leaks. memory allocation, tons of problems, throttling, you name it, it happens, and it's very quiet. So it also affects pooling too. You'll notice I had multiple connections. Luckily, if it was a server with just one connection, it can only take one request, send it back. I mean, it's like nothing's ever going to work. So I've already explained these guys already, so I'm just going to skip it. So how do you remedy close waits? Like, what's the fix? You notice that for me to fix it, I have to go into the code. But in some cases, I can't. So whenever you get close waits, you just have to either, one, find the bug in the code. Now, this is bad, especially if you're on Redis, Postgres, where like you don't even have access to the code to begin with. They just give you a binary, and the binary is buggy. So that's why it's so hard to fix. Because you need to fix the server, because TCP said what? The client is always right. Literally. So you get to this point, you push on, you push on, you push on. The only way to fix it is you wake up and you run this command to kill everything. So this is actually the end of it all. There are manifestation of bad requests, either the client or the server, and it's just a good idea to monitor it where you can. So these are some notes I have. Time is up. And yeah, that is all for me. Thank you all so much. Oh, yes.
Okay, so this close weight, right, or this particular socket now. So because you're using or is associated with basically with TCP, right, with the whole handshake and everything, I'm trying to know if it actually opens up any form of security vulnerabilities, right?
You are very spot on. So you notice that when I was making those requests, you notice that every time I made a new request, there was a new process I was running.
Yeah.
Now imagine if that was someone's password in memory, sitting there quietly for somebody to go, reap and... So yeah, it opens up a lot of problems. Not just security, but even usage itself, because every time someone makes a new request, there's metadata left on there. The server allocated resources to handle the request. There's memory leaks because those things don't close. So they are just running there. Imagine if it was S3, you're sending a file, right? Because S3, they don't send the file at once. They open multiple parallel connections and then stream different partitions of the file up to the server. That means that one request opens up like what? Hundreds of them with user files, partitioned, corruption. You cannot see where I'm going. If that one socket failed, the entire file is corrupted. So it opens up a lot of problems. Security, even just consistency in that case. So yes, you are correct. Okay, thank you. Oh, thank you.